After learning some basic concepts and operations of linear algebra, let's see the linear transformation and the metric. Linear algebra can be regarded as the study of discussing space transformation and vector motion, which are both achieved by a linear transformation. Suppose that Vn is an n-dimensional linear space and Un is an n-dimensional linear space. The transformation T is a mapping from Vn to Un. T can be regarded as a linear mapping or a linear transformation if the following two conditions are satisfied. It is suitable for any vectors alpha and lambda. A linear transformation is often used in AI computer vision by translating, rotating, or scaling original images to generate a new image to augment the dataset. Since linear transformation is important, we have an example which can be used in AI computer vision to pre-process image data. Here, the random point P is the vector, while the linear transformation A1, A2, A3, we can get a new point by metric multiplication. For example, A1 multiply the vector P, so we get the new point P, X minus Y. The other two, A2 and A3, are do the same metric multiplication. To visualize the linear transformation, we can look at three graphs to check how point P is transferred into the new point P using the corresponding transformation matrix A. Like A1, the point P lands on its reflection, new point P across the x-axis. It is called the reflection transformation, and A2 can do the scaling transformation. The distance from the new P2 to the original point 0, 0 is the value lambda. As for the last one, A3, with the angle theta, it is a common transformation in Euclidean geometry. It's to rotate the plane around the original point. Think of Euclidean points as vectors in a vector space, and rotation can be viewed in the sense of linear algebra. This figure shows the point P rotating counterclock in the angle theta. That's what we call the rotation transformation. In linear space, a metric represents a linear transformation, such as rotation, scaling, and reflection. Vectors are transformed by metric multiplication. After learning the linear transformation, let's go back to see the matrix-related matrix transposition. The transpose of a matrix is a new matrix which rows are the columns of the original matrix. Here are a matrix and its transpose. The superscript T means the transpose. It turns the columns of the new matrix into the rows of original matrix. Following the basic operations of the matrix and its transpose matrix. Here is the new matrix, diagonal matrix. It is a matrix where all the elements are 0 except the mean diagonal. The properties of the diagonal matrix is which the sum, difference, product, and power of the diagonal matrix are those of the entries on the main diagonal. If the elements on the main diagonal are the inverse of the corresponding element on the main diagonal of D, then D is a diagonal matrix. Besides, the transpose of the diagonal matrix D is the same matrix. From these probabilities, we can see the diagonal matrix can reduce the computational cost. On this page, we have some new metric: identity metric, inverse metric, and orthogonal metric. The identity metric of size m is also called the unit metric. Here is the m by m square metric, where ones are on the main diagonal and zeros are elsewhere. IM is the example of the diagonal metric. AI equals IA equals A, which means product of any square matrix, and the appropriate identity matrix is always equal to the original matrix, no matter where the multiplication performed. The inverse of a number is reciprocal. For example, the inverse of 8 is 1 in 8. Therefore, a number multiplied by its inverse will always equal 1. The inverse of a matrix A is another matrix denoted by the A minus 1 and can be defined as the A minus 1 times A equals to IN. IN is the identity matrix. So just like a number multiplies its inverse is always equal to 1, a matrix multiplies its inverse is equal to the identity matrix. So what about the orthogonal matrix? If its transpose is equal to its inverse matrix, we can say the square matrix with real numbers or elements is the orthogonal matrix. Next, we will see the symmetric matrix. It's a square matrix that is equal to its transpose. For example, the distance matrix and the covariance matrix are both symmetric matrices. We can see the distance matrix is the symmetric around the main diagonal 1.2, 2.2, and 2.5.